In this presentation, I'm going to discuss experimental design. And ideally, the purpose behind experimental design is that as engineers, we design experiments so that we can effectively and efficiently assess the impact that certain factors, certain things have on the processes or systems or performance of certain things or material lifespan of whatever it is that we're trying to measure. And we've already encountered certain types of experimental design. For example, hypothesis testing, t-tests, ANOVAs. These are different ways in which experiments are designed so that you can, basically ask some hypothesis or have some hypotheses and test them and actually see if what you're trying to test is true or not. And in what we've primarily done before this is that we've done comparisons. And what we've essentially tried to do is we've tried to compare certain populations or samples of populations to see if they're typically either equal or not equal to each other, which is the foundation of what we define in our hypothesis test. And using that information, we can, make inferences about data that we can, sort of understand in the future. So as an engineer, when you actually conduct any type of experiment, you want to make sure that you do a few things. And the first thing is you want to make sure that when you collect your samples that you are randomly selecting them. You don't want to go in and just arbitrarily choose the first 10 data points that come along. In fact, you want to go in and actually randomly select data points so that you are getting a better sampling of the data. If you don't do that, you could potentially bias your data. So for example, let's say you're conducting an experiment where you're measuring the temperature effects on battery performance in a car. And your first 10 data points, your device that you're using to measure the performance of your battery hasn't warmed up fully yet. And so if you choose those data points, you're going to bias your sample incorrectly. Whereas if you had gone in and you had taken all the data that you had collected over, let's say, 2 weeks, and randomly chose, points along the, various points along each day and for each day, then you're getting a better sample of your data that you can actually run some analysis on. The other thing you want to do is you want to do replicates. In engineering or in science, you typically do everything in threes. Everything should be done in triplicate. 3 doesn't necessarily have to be the magic number. I think 3 is a typical, beginning level. So if you want to test it out 10 different times just to make sure that your data is robust and that the claims that you're making with your data are justifiable, then by all means do it. So in this week's world, our next type of experimental design is called a factorial design. And the idea behind a factorial design is that we essentially are going to look at the effects of a single factor in our sample and the possible interaction that several factors may have. So we can line up different factors and see if a single factor is really impacting everything, or maybe it's the interaction, or maybe multiple factors are looking at things. And you can see by sort of setting up the experiment that way, we're more efficiently going in and assessing things versus just doing one test at a time. So what does this actually look like? So basically, I'm going to use an example where we're trying to understand the durability of paint on our cars. So basically we have a couple of different factors. The first one is, is the sun out or not? The second one is, cold, hot, or temperature. The third one is wet and dry. And then the last factor is, rock salt. And so what we do when we set up these experiments for a simple factorial design, in this case it's a 2 factorial design, because what we're going to do is we're going to split our options into 2. So for sun, it can either be sunny or it cannot be sunny. So maybe it's a cloudy day. It can be hot or cold. And as an engineer, we would set limits. So maybe cold, which is 0, is equal to 15°C, and hot is, or anything less than 15°C, and hot is anything greater than 15°C. Wet, dry, does it rain that day or does it not rain that day? So again, does it rain? Yes. No. Rock salt. Was rock salt on the roads that day? So you can see it's kind of set up in a binary type system, but it doesn't have to be in 0s and 1s. And actually, a lot of times, we see this set up as contrast levels, which we would just do contrast of 1 to -1, or 1 to -1 for each option. So you can see that as we measure durability each day, it has, the car has the option of being exposed to these different things. So maybe it was sunny today, and it was pretty hot and dry, and there was no rock salt. And so that's just sort of one iteration, or one day's worth of data. And what we actually measure for each day is that durability value. So we measure durability, but it can be the sort of conditions that the car could be under can have many, or like a factorial type scenario. And so once we sort of understand what this design could look like, we can do some analyses, typically in Minitab, because that's the easiest way to do it. But we can also do it in Excel if we don't want to use Minitab that day. And at the end, what we're able to do is we're able to isolate the effects that each factor have on the durability of the car. So it could be that sunlight and rock salt are a very significant effect, or have a very significant effect on the car's paint durability. And we also could look and say, oh, there are also interaction effects of each factor pair. And so maybe it's that when it's wet out and you put rock salt on the car, that they interact together, and that's when you see the durability of your car's paint go down significantly. So that's kind of the idea behind what we're going to be doing this week when we're talking about experimental design, and I hope you have a better understanding of what that means. Thanks.